So this is part 3, graphing rational functions. So as you can see here, it's f of x is equal to 3x squared plus 3x minus 6 all over x squared plus x minus 12. So looking at this function again, we always want to look at if there are holes or not. And so in order to do that, we must factor out both the values in the numerator and in the denominator if it's possible. So let's think of two numbers that have a product of negative 18 and a sum of 3, right? And we see that's 6 and negative 3, really. If we factor this out, I mean, really, we can just write this as 3x squared plus 6x minus 3x, right? Because 6 and negative 3, product negative 18, sum plus 3. And we write that 6x minus 3x, and then it's minus 6. Factor this out, we get 3x, so we get 3x times x plus 2, and then we have minus 3 times x plus 2 here. So that's again 3x minus 3 times x plus 2, right? And we really can even factor this out. You get 3 times x minus 1 times x plus 2. So this is what we have, and I'm just going to erase this quickly, and then, so we have this value here, right? So simplifying this, we had 3 times x minus 1 times x plus 2. That's the value we had. And looking at the denominator again, thinking of two numbers that have a product of negative 12 and a sum of 1, we should realize that is 4 and negative 3. And for this one, we can just directly do it because again, the coefficient of x squared is just 1. So that's just x plus 4 times by x minus 3. Right, so those are the two factors that we have here. Now, this is what we have. Now, do we see any factors that can be cancelled off, right? Those factors that could possibly be common in the numerator and in the denominator. And I don't see anything. I see that these two factors are the distinct factors in the denominator. And again, because they're distinct factors, that indicates that there are vertical asymptotes at these points. So let's set each factor to 0. So if x plus 4 is equal to 0, right, we have a vertical asymptote at negative 4. So we say that there's a vertical asymptote, right, at x is equal to negative 4 and at x is equal to 3. So we have two vertical asymptotes here. And so those are our vertical asymptotes, and the fact that we really can't remove any commonalities because there are no common factors, the holes in this case would be not applicable here. And now we have the horizontal asymptotes, right? So with horizontal asymptotes, again, we just look at our original function and seeing really nothing crossed off. So we just look at the original function, and 3x squared over x squared, again, x squared, they have the same degree of 2. Therefore, we're just doing a over b. In this case, a over b is 3 over 1. That's just 3. So we have a horizontal asymptote at y is equal to 3. If you remember, if there was a degree here, I'm just revising that topic, that idea, the rule that if your degree here was greater, if it was like x to the power of 5, then your horizontal asymptote would have been y is equal to 0. However, if it was only x, right, or if it was less than x squared, then we would actually have to divide the numerator by the denominator, and in that case the horizontal asymptote would not be applicable. We would have a slant asymptote, which I'll go later in more depth in the next lesson. So this is what we have so far. And now looking at the x-intercepts, that's the value of x when y is 0, right? So now when y is 0, right, that indicates that the value in the numerator must be 0. So we have this as the factored form, and if we think about it, this can be 0 and this can be 0, right? If we set this factor to 0 and this factor to 0, we see that the value in the numerator is also 0. And so doing that, we see that there are two x-intercepts actually. One is at 1, comma 0, and the other one is at negative 2, comma 0. So 1 comma 0 and negative 2 comma 0. With a y-intercept, it's the value of y when x is set to 0, and we can really do it it won't matter where we substitute that 0 in. If we do it here, we see it's negative 1 times 3, that's negative 3. Then we are multiplying that by 2, divided by 4 times negative 3. So we really have negative 6 divided by negative 12. That is 1/2. So our y-intercept is 0, 1/2. Right, and our domain is now the set of all real numbers, right? It's the set of all real numbers such that x is not equal to negative 4 or 3. And the reason for this is, again, because negative 4 and 3 are vertical asymptotes, right? There are vertical asymptotes at x is equal to negative 4 and at x is equal to 3. Therefore, within the domain, you will not be including those values. So now this is our given information, right? We have everything. Now we can graph it. So let's graph this function here. Again, we had negative 2, 0, right, for the x-intercept. So again, let's graph. This is the x, this is the y. And always look at your asymptotes, right? They're easy to graph. So we know that we have a horizontal asymptote at y is equal to 3. Right, and then we have a vertical asymptote at x is equal to negative 4, and we have another vertical asymptote at x is equal to 3. So something like that, I guess, just an approximation. So we know this is 3, this is negative 4, and then you could say that this value here would be something like 3, right? And so now we have that, and we really want to look at our x-intercepts. So our x-intercepts were 1, 0, right? So we can plot that here. And then we also had negative 2, 0 as our point here. We can substitute more values in to see, some values of x here. But if you do that, you should understand that it's not really possible to get something like this, because if we had a value here, really we would be seeing that this value must be connected to this value. That's not possible because we have a horizontal asymptote. I mean, that could be possible if you were crossing the horizontal asymptote, again, which I said is possible. You cannot cross a vertical asymptote. You can cross a horizontal or a slant asymptote. However, in this one, you can substitute a value in, but you will see that you'll get some value that's here and another value that's here. So that indicates that our graph looks something like that. So that's where it is. Now we have to think about points that are beyond or points that are less than negative 4 and points that are greater than 3 to see where the graph lies for such points. And looking at it, so really you can substitute anything, but if you were to substitute negative 5, negative 6, usually what I prefer is I will not directly substitute those values in for the original equation. If I am able to factor it out, it just makes it much more easier to actually multiply them and then divide it. So I do recommend that, but after you substitute the values in, you can type those in your calculator. You will see that it gives you something like that. And when you have something like this and you plug in 4, 5, 6, you'll see that that gives you a graph like that. So really this is our graph here. You have one here, you will have one. So you see that those 3 asymptotes, the graph is really never approaching, I mean, it's not really touching those asymptotes. It is approaching and it's tending towards those asymptotes. So this is what we have here. Now there's another concept, and that is of limits. And I didn't really go over limits in part 2 and part 1 because you really wanted to reinforce your graphing skills. But the limit idea I can quickly explain. So this is the graph we have, so I'll just erase this quickly. And with the idea of limits, right, again, when you're looking, you have asymptotes, you have that concept of limit. And what limit just really means, again, it's something, again, the graph is approaching a particular value. It's approaching that value. It's not quite touching it. It's just tending towards that value. So when you write this as a notation, you would say that limit as x approaches infinity of f of x is equal to what? Or I may have something like limit as x approaches 6 of f of x is equal to what? And so these are just some practice problems so that your mind starts thinking in that direction. Again, limits are the basis of calculus. Looking at this, x approaches infinity, right? So let's think about this. As x approaches infinity, so we go here and we continue to go towards the right direction forever, right? We continue going there. This graph will constantly continue to go like this. Now it's never going to touch the this asymptote here, the horizontal asymptote that we had at y is equal to 3. It's not going to touch that. It could, I mean, again, you can check by seeing if it crosses or not, but most likely it's not going to be touching. It's just going to be approaching that asymptote. It's not going to actually touch or cross it. Again, you could check if it crosses it or not, but really, so if you want to check it, let me just make it clear. If you want to check it, what you really do is you have y is equal to 3, right? So if you want to see if it crosses or not, you take 3, right, and you want to put 3 in for f of x, and then you have 3x squared, right, plus 3x minus 6, and then this thing, we can just multiply that here, x squared plus x minus 12. So we're multiplying this by 3, that gives us 3x squared plus 3x minus 36. It should be this, right? 3x squared, 3x cancel, 3x go away. So really, we're left with 0x, right, 0x, and remove the 36 that side, so that gives us 30, and so really we have 0x is equal to 30, and x is equal to 30 over 0, and the fact that we get an undefined value indicates that there's no such crossing, although crossing can happen. In this scenario, there's no crossing, and so that indicates that the limit of f of x as x approaches infinity, right, is just 3. Because that's the value that we're approaching. Now if you have something like limit of f of x as x approaches 6, now at times what happens is, you know, it may not be approaching, it may be at that point exact. What I mean by that is that at 6, right, we can really substitute 6 into the equation, and we see that there's a point that the graph crosses, and really that is the point. So in that case, you're just substituting 6 into the equation, and doing that on your calculator, you'll see that that gives you 4. So really 6 comma 4 is a point here somewhere where that point actually exists for f of x, and so it doesn't necessarily have to be approaching. If it could be a point where you're just directly substituting 6 into the equation. However, when you had a limit of f of x as x approaches infinity, it was quite clear that as your graph approaches infinity, the y value that is being approached is 3. So thanks for watching, and again, in the later lesson I have a few more complex rational functions that need to be graphed. So thanks for watching.